And now in this lecture we find out the radius of the small circle. In the drawing we have the right angle ABC. Side AB equals to 6 units in half, side BC equals to 8 units in half. This is angle ABC, that is the right angle. Inside this right big triangle ABC we have this small circle, and we have this big semicircle, and our mission is to find out the radius of this small circle. So first of all, we'll implement the Pythagoras theorem on this right big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. So I write it down. Here by PT is the abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle ABC, AC square, that is the square of the hypotenuse, must be equal to AB square plus BC square. Repeat again, according to the Pythagoras theorem, in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in conclusion, we found out that AC square equals to 36 plus 64, that is 100. So AC square equals to 100. We take out all of this equation and finally found out that AC equals to the square root of 100, that is 10. So actually the length of the hypotenuse AC is 10 units, so write it down. AC equals to 10 units in its length. In the next step, we define the relevant points to this question with letters. We define the center of this small circle, this point is point P. We define the center of this big semicircle, this point is point Q. We define the point of tendency of tangent AC with this small circle, this point is point K. We define the point of tendency of tangent AB with this small circle, this point is point N. We define the point of tendency of tangent AC with this semicircle, this point is point H. And finally, we define the touching point of this small circle with this big semicircle, this point is point L. Here we can implement rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. If we focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. So write it down. According to rule 2, AB equals to AH. But AB is 6 according to what is given as the question. So I can write here that AB is 6, and from this equation 6 equals to AB equals to AH. We derive that AH is also equals to 6 units in its length. Okay, this is side AH and is equals to 6 units in its length. So write it down. AH equals to 6 units in its length. What is the length of line segment HC? From the drawing it is very easy to see that HC equals to AC minus AH. Again, AC minus AH equals to HC. So HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. So I write it down, HC equals to 4 units in its length. In the next step, we join points Q and H together by straight line. Point Q is the center of this big semicircle. Point H is the point on the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of the big semicircle as B. So QH is B. Is the radius of the big semicircle. Here we can implement rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. We have the radius QH is equals to B. The radius QH is drawn to point H. That is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius QH. If AC is perpendicular to QH, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can here the right angle QHC. The right angle QHC, we have this angle, angle C. But this angle C is a common angle that belongs also to the right big triangle, triangle ABC. So we define the size of this common angle, angle C, as alpha. So in the right small triangle HQC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on the right big triangle ABC. In the right big triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that the right big triangle ABC is similar to the right small triangle HQC. So why the big right triangle ABC is similar to this small right triangle HQC? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC, the right big triangle ABC. And it is equal to this angle. That is actually angle QHC. And the right small triangle HQC. So I repeat again. I actually found out that angle ABC in the right big triangle ABC equals to angle QHC in the right small triangle HCQ. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. If we relate to angle alpha as it is belongs to the big triangle ABC, it will be defined as angle ACB. And it equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle HQC, it will be defined as angle HCQ. And again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle BAC. In the right big triangle ABC, and it is equals to this angle. This is actually angle HQC. In the small right triangle HCQ. So I repeat again. Angle BAC in the right big triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of the right triangle HQC. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. I actually found out that the right big triangle ABC is similar to, this is the sign of similar, to the right small triangle HCQ according to angle similarity rule. And from the fact that the right triangle ABC is similar to this right small triangle HCQ, we derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Repeat again. We derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the right small triangle HCQ. AB is 6 over HQ. HQ is B, it is the radius of this big semicircle, and it is equals to BC. BC is 8. BC is 8. According to what is given as the question, over HC. We already found out that HC equals to 4 units in its length. So in conclusion, we should find out that 6 over b equals to 8 over 4. 8 over 4 is 2. So actually found out that 6 over b equals to 2. We multiplied this equation by b and finally found out that 6 equals to 2b. Here we divide this equation by 2 and finally found out that the missing radius b equals to 6 over 2, that is 3. So actually found out that the radius of this big semicircle b equals to 3 units in its length. Point Q is the center of this big semicircle. Point B is the point of the big semicircle itself. Therefore, QB is the radius of this big semicircle that equals to 3 units in its length. In the next step, we join points P and L together by a straight line. Point P is the center of this small circle. Point N is the point of the small circle itself. Therefore, Pn is the radius of this small circle. That is the radius that we are looking for in this question. We will define the radius of this small circle as A. Therefore, Pn equals to A. This is the radius of the small circle. So here we have the radius Pn is equals to A. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by a straight line. PK is of course the radius of this small circle, that is equals to A. Again, the radius PK is drawn to point K, that is the point of tendency of tangent AC with this small circle. Whenever your radius is drawn to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to the same rule, rule 1. In the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you will draw two tangents to that circle, then the angle that will be created between the two tangents, its angle bisector, must pass for the center of the circle. So here, this is the circle, and here, this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. By drawing the two tangent PA and PB to this circle, we created here angle APB. Again, angle APB was created by drawing tangent PA and tangent PB from this common external point, point P. And according to this rule 15, the angle bisector of angle PAB, this is angle PAB, so the angle bisector of this angle APB, the angle bisector of this angle APB passes from point O, that is the center of this circle. Again, whenever you draw two tangents from a common standpoint towards a circle, then the angle bisector that was created by the two tangents must pass for the center of the circle. In this case, by drawing the two tangents PA and PB from the common standpoint point B, we created angle APB. The angle bisector of angle APB, the angle bisector of this angle must pass through point O, that is the center of this circle. So we can actually implement all 15 in our drawing. Why? Because in our drawing, if you focus on this common standpoint point A, from this common standpoint point A, we have two tangents to this small circle, tangent AN and tangent AK. So by drawing the two tangents AN and AK, we created this angle A. Again, this angle A was created by drawing tangent AN and AK towards this small circle. And according to rule 15, the angle bisector of this angle A must pass from point B, that is the center of this small circle. Because again, the angle bisector of angle A that was created by drawing tangent AN and tangent AK to this circle, the angle bisector of this angle A must pass through point B, that is the center of this small circle. So here you can see that the angle bisector PA, of course, passes from point P, that is the center of this small circle. If we define the size of this angle A is 2 theta, then the angle bisector PA bisects angle A into 2 halves. Each half must be equal to theta, of course. So we can write down that the angle bisector of angle A passes through point P, that is the center of this small circle. So I write it down. I can find out that the angle bisector of angle A passes for point P, that is the center of the small circle. This is of course according to rule 15. Likewise, we'll continue to focus on this common standpoint point A. From this common standpoint point A, we have two tangents towards this big semicircle, tangent AB and tangent AH. Actually, by drawing the two tangents AB and AH, we can achieve the same angle A. Again, angle A was created by drawing tangent AB and tangent AH to this big semicircle. So now we can implement all 15. Whenever we have two tangents from a common standpoint to a circle towards a circle or semicircle, you can implement all 15. According to rule 15, the angle bisector of this angle A that was created by drawing tangent AB and AH towards this semicircle, then angle bisector of this A must pass from point Q, that is the center of this big semicircle. Again, the angle bisector of this angle A must pass from point Q, that is the center of this big semicircle. So I draw the angle bisector QA of this angle A. Again, here QA is the angle bisector of angle A, and QA, the angular sector QA passes of course through point Q, that is the center of this big semicircle. So I write it down. Actually found out that the angle bisector of the same angle, angle A, angle bisector of the same angle, angle A, passes also through point Q, that is the center of the big semicircle. Okay, but it is obvious that the angle bisector of this angle A passes also through point A. So write it down. The angle bisector of the same angle, angle A, passes also for point A. Again, the angle bisector of this angle, angle A, passes for point A, of course. So in conclusion, we can find out that the angle bisector of this angle A passes through points A, P, and Q. So I write it down. In conclusion, we found out that the angle bisector of angle A passes through points A, P, and Q. And again, the angle bisector of this angle, the angle bisector of this angle, angle A, passes through points A, P, and Q. But the angle bisector of any angle is a straight line. Again, the angle bisector of any angle is a straight line, and especially the angle bisector of this angle is a straight line. And therefore we can write down that all the points A, P, and Q, they are all passing through the straight line of the angle bisector of angle A, or all the 3 points A, P, and Q, they are all located on the straight line. The points A, P, and Q, they are all located on the same straight line. And the straight line is the angle bisector of angle A. Okay, writing down the straight line is the angle receptor of angle A. So we found out that all the 3 points A, P and Q are located on the same straight line. So we can write down also that line segment APQ is one straight line. Again, line segment APQ is one straight line. Line segment APQ is one straight line and if line segment APQ is one straight line, it means that AQ is a straight line. AQ is a straight line and if AQ is a straight line, it means that shape ABQ is a right angle. Again, shape ABQ is a right angle. So I write it down. And conclude from it that shape ABQ is a right angle. So in the right triangle ABQ, this is angle theta. Again, in the right triangle ABQ, this is angle theta. But this angle theta is a common angle that belongs also to the right small triangle A and P. Again, I shall find out that angle theta is a common angle that belongs to both triangles, triangle A and P, in the big triangle ABQ. Okay, so in the right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this third angle must be equal to 90 degrees minus theta. So I write it down, this third angle must be equal to 90 degrees minus theta, why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. According to the same rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right big triangle ABQ is similar to this small right triangle A and P. So I write it down. We prove that the right big triangle ABQ is similar to this small right triangle A and P. So why the right triangle ABQ is similar to the right small triangle ANP? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABQ, in the right big triangle ABQ, and it is equal to this angle, that is actually angle ANP, in the right small triangle APN. And then again, if we found out that angle ABQ, the right triangle ABQ equals to angle ANP, the right big triangle APN, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. So you can write down that angle theta equals to itself, it's a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the right big triangle ABQ, it will be defined as angle BAQ. And it is equals to itself. So if we relate to angle theta as it belongs to the right small triangle ANP, it will be defined as angle NAP. Repeat again. This equation means that angle theta equals to itself. We just called to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is angle AQB. The right big triangle ABQ, and it is equals to this angle, that is actually angle APN, the right small triangle ANP. And this again, we should found out that angle AQB in the right big triangle ABQ equals to angle APN in the right small triangle ANP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So if we found out that all the fingers in the right big triangle ABQ are correspondingly equal to all the fingers in the right big triangle in the right small triangle ANP, and therefore those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. So the right big triangle ABQ is similar. This is the sign of similar to the right small triangle ANP according to angle similarity rule. And for the fact that the right big triangle ABQ is similar to the right small triangle ANP, we derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. And again, we derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB equals to 6 over AN. AN is the missing side, so we will leave it as it is. And it is equals to BQ. BQ equals to 3, it is the radius of the big semicircle. This is equals to 3 units in length over NP. NP equals to A. A is the radius of this small circle. That is the radius that we are looking for in this question. So in conclusion, if we found out that 6 over AN equals to 3 over A. Here we cross multiply this equation. Finally we get that 6A equals to 3AN. Here we divide this equation by 3 and finally we get that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So if we found out that the missing side AN equals to 2A units in its length. So I write it down. The missing side AN equals to 2A. So actually AB equals to 6, AN equals to 2A. Therefore the missing 9/7 NB must be equal to AB minus AN. AB is 6, AN is 2A, so in total NB equals to 6 minus 2A. So I write it down. Actually found out that the length of 9/7 NB equals to 6 minus 2A units in its length. The next step, we do a construction, that is to say, from the center of this small circle, that is to say from point P, we will go perpendicular on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we can do quadrilateral NP-BZ. Inside quadrilateral NP-BZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NP-BZ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NP-BZ as a rectangle because it has 4 right angles. So I write it down. Quadrilateral NP-BZ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPZB, side NP must be equal to the opposite side BZ, but NP is A, therefore BZ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPZB, side NB must be equal to the opposite side PZ, but NB equals to 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of the missing side ZQ? ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. BQ is 3, BZ is 8, so in total ZQ equals to 3 minus A. So I write it down, ZQ equals to 3 minus A. What is the length of line 7 PQ? Actually, we find out the length of line 7 PQ by implementing rule 10 in our drawing. In our drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally and this point L. And whenever you have an external notch between two circles, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching point. In the drawing, we have two circles and they touch each other externally in this point P. Therefore, here the center of this small circle is at point M. The center of this big circle is at point O. And the straight line that connects the centers together is the straight line MO. So this straight line MO must pass from point P, that is the touching point. I repeat again, this straight line MO must pass from point P, that is the touching point. Or MPO is one straight line. Again, MPO is one straight line according to this rule 10. You can actually implement rule 10 in our drawing. Why? Because in our drawing, you have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at point L. The center of this small circle is there at point P. The center of this big semicircle is there at point Q. And the straight line that connects their centers together is of course the straight line PQ. And this straight line PQ, according to rule 10, must pass from point L. Again, this straight line PQ must pass from point L, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line according to rule 10. If PLQ is one straight line, it means that PQ is a straight line. And what is the length of PQ? PQ equals to PL plus LQ. Again, PQ equals to PL plus LQ. So I write it down. We actually found out that PQ equals to PL plus LQ. Why? Because PLQ is one straight line, according to rule 10. So PQ equals to PL. PL is the radius of this small circle, that is equals to A, that is the radius that you are looking for in this question, plus LQ. LQ is the radius of this big semicircle, that is equals to 3. So in total, PQ equals to PL, that is A, plus LQ, that is 3. So in total, PQ equals to A plus 3 units in its length. In the next step, I'll copy the right green triangle PZQ in the new page, and we will implement the Pythagoras theorem on this right green triangle PZQ. Here by PT is a promotion for Pythagoras theorem. So actually this is the right green triangle PZQ that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. So write it down. PQ square, that is the square of the hypotenuse, must be equal to PZ square plus ZQ square. PQ, the hypotenuse PQ is 3 plus a, therefore PQ square is 3 plus a square. And it equals to PZ square. PZ is 6 minus 2a, therefore PZ is 6 minus 2a square. Plus ZQ square. ZQ is 3 minus a, therefore ZQ square is 3 minus a square. So if we found out that according to the Pythagoras theorem, 3 plus a square equals to 6 minus 2a square plus 3 minus a square. Here we'll open the brackets on both sides of this equation and find out actually that 3 plus a square is 3 squared, that is 9, plus a square plus 2 times 3 times a is 6a. And it is equal to on the other side of the equation we have 6 squared, that is 36, plus 2a squared is 4a squared, minus 2 times 6 is minus 12, and minus 12 times 2a is minus 24a. Plus 3 minus a square. 3 minus a square equals to 3 squared, that is 9, plus a square, minus 2 times 3 times a is minus 6a. So here we have 9 on both sides of the equation, so 9 will get cancelled. We have also a square on both sides of the equation, so a square also will get cancelled. So after cancelling those two expressions, in this side of the equation we have only with 6a. In the other side of the equation we have 36 plus 4a squared here minus 24a minus 24a minus 6a is minus 38. So if we found out that 6a equals to 36 plus 4a squared plus 38. Here we subtract 6a from this equation. And again, after we subtracted 6a, in this side of the equation we have nothing, that is to say 0. On the other side of the equation we have 36 plus 4a squared was 48. So plus 4a squared, and we have here minus 38 minus 6a is minus 36a. In conclusion, we found out that 0 equals to 36 plus 4a squared minus 46a. Here we divide this equation by 4. And we get that 4a squared over a squared is a squared. 4a squared over 4 is a squared. We have minus 46a over 4 is minus 9a. And 36 over 4 is 9. 0 over 4 is 0. So in conclusion, we found out that a squared minus 9a plus 9 equals to 0. So actually, this is a quadratic equation. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, this is to say a squared minus 9a plus 9 equals to 0. The variable that we are looking for is a, so x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 9. And the coefficient equals to 9. Now the only thing that is left to do is to put the data from our specific quadratic equation inside this general formula for x, and we will find out the value of the values of a, because x equals to a. So we will do it now, and we will get that x equals to a, so a equals to minus b is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a is 1, so minus 4 times 1 is minus 4 times c is minus 9, c is 9, therefore minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 over 2a. A is 1, so 2 times a is 2 times 1, that is 2. So if we found out that a equals to 9 plus minus, inside the root we have 81 minus 36. 81 minus 36 is 45 divided by 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2. This expression 9 plus square root of 5 plus square root of 45 over 2 is greater than 3. A is the radius of the small semicircle. But actually, the radius of this small circle A cannot be greater than 3. Why? Because of the fact that the radius of the big semicircle equals to 3 units, and the big circle is definitely bigger than the small semicircle. And therefore, the radius of the big semicircle must be bigger than the radius of this small circle. Or in other words, the radius of the small circle must be smaller than 3, that is the radius of the big semicircle. But this, so this solution that gives us the radius of the small circle A is greater than 3 is the correct solution, because the radius of the small circle must be less than 3. So we cancel the solution, and we left only the second solution that is possible for A. The second solution for A is that A equals to 9 minus equal to 45 over 2. A equals to 9 minus 45 is 9 times 5, so we substitute 45 by 9 times 5 divided by 2. So A equals to 9 minus the square root of 9 is 3, so inside the root we left only with 5 divided by 2. So actually found out that we're going to do the second solution for A equals to either 9 minus 3 times square root of 5 over 2 units in itself, or in terms of numbers, the radius A of the small semicircle equals to 1.146 units in its length. Repeat again, actually I found out that the radius A of this small circle equals to either 9 minus square root of the radius A of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, so in terms of numbers, the radius A of this small circle equals to 1.146 units. So in the next step, I'll summarize the lecture. In this lecture, we found out the radius of this small circle. So in the domain, we have the right triangle ABC. We know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. In addition, inside this big right triangle ABC, we have this small circle and we have this big semicircle. Our mission is to find out the radius of this small circle. So first of all, we implemented the Pythagoras theorem in the right triangle ABC. According to the Pythagoras theorem, it is true in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. Repeat again, according to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is, so AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total, AC square equals to 36 plus 64, that is 100. So AC square equals to 100. We took out of this equation and finally found out that the missing hypotenuse AC equals to the square root of 100, that is 10. So the length of the hypotenuse AC is 10 units. In the next step, we define the relevant points to this question with letters. We define the center of this small circle, this point as point P. We define the center of this big semicircle, this point as point Q. We defined the point of tendency of tangent AB with this small circle, this point as point N. We define the point of tendency of tangent AC with this small circle, this point as point K. We define the point of tendency of tangent AC with this big semicircle, this point as point H. And finally, we define the touching point between this small circle and this big semicircle, this point as point L. Here, we implemented rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So here we have, this is the common external point, point A. From this common external point, point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. Repeat again. According to rule 2, AB equals to AH. But AB equals to 6 units in itself, according to what is given as the equation. So you can write it that AB equals to 6, and from this equation 6 equals to AB equals to AH, we will derive that AH also equals to 6 units in itself. This is line 7 AH is equals to 6 units in itself. What is the graph of line 7 HC? From the law it is very easy to see that HC equals to AC minus AH. Again, HC equals to AC minus AH. So HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. In the next step, we join points Q and H together by side line. Point Q is the center of the big semicircle, point H is the point of the big semicircle itself, therefore QH is the radius of this big semicircle. We define the radius of this big semicircle as B, therefore QH equals to B. Here we can implement rule 1, because according to rule 1, a tangent to the circle is perpendicular to the radius to each point of tendency. We have here the radius QH that is equals to B. The radius QH is 1 to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever we have radius that is 1 to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. So, when doing this construction, we're going to do the right triangle QHC. The right triangle QHC, we have this angle C, but this angle C, it is a common angle that belongs also to the right big triangle ABC. So we define the size of this angle C as alpha. So in the right triangle HQC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, if we focus on the right triangle ABC, on the right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that the right big triangle ABC is similar to the right small triangle HQC. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so you can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the three angles in the right big triangle ABC are correspondingly equal to all the fingers in the small right triangle HQC, therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again, we actually found out that the right big triangle ABC is similar, this is the sign of similar, to the right small triangle HCQ according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. It again, we derive that side AB in the big right triangle ABC or side HQ in the small right triangle HCQ equals to side BC, the big right triangle ABC, or side HC in the right small triangle HCQ. AB is 6, AB is 6, over HQ. HQ is B, it is the radius of the big semicircle, that is B, and it is equal to BC. BC is 8 over HC. We already found out that HC equals to 4. So if we found out that 6 over B equals to 8 over 4, 8 over 4 is 2. So if we found out that 6 over 4 equals to 2. We multiplied this equation by B and finally found out that 6 equals to 2B. Here we divided this equation by 2 and finally found out that B equals to 6 over 2 is 3. So the radius B of this big semicircle equals to 3 units in its length. Point Q is the center of this big semicircle. Point B is the point on the big semicircle itself. So for QB is the radius of this big semicircle, and the radius equals to B, that is 3. So QB equals to 3 units in its length. In the next step, we join points P and N together by a straight line. Point P is the center of this small circle, point N is the point on the small circle itself, therefore Pn is the radius of this small circle. We define the radius of this small circle as A, therefore Pn equals to A. A is the radius that we are looking for in this question. Here we can implement rule 1, because we have the radius Pn, that is 1 to point N, that is the point of tendency of tangent AB with this small circle. And whenever we have radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and Q we join points P and K together by a straight line. PK is the radius of this small circle, that is equals to A. We have the radius PK, that is 1 to point K, that is the point of tendency of tangent AC with this small circle. And whenever you have radius that is 1 to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle, you draw two tangents to that circle, then the angle that will be created between the two tangents. Here we have, this is the common external point, point P. From this common external point, point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents, we can get here angle APB. Again, angle APB was created by drawing tangent PA and tangent PB to this circle. Actually, the angle bisector of angle APB, the angle bisector of this angle APB, must pass through point O, that is the center of this circle. Again, the angle bisector of angle APB that was created by drawing the two tangents PA and PB to this circle, then the angle bisector of this angle APB must pass through point O, that is the center of this circle. So whenever you draw from a common external point, from any common external point to a circle, two tangents to this circle, then you get an angle, and the angle bisector of the angle that is created by drawing the two tangents from a common external point to a circle towards the circle, the angle bisector of that angle must pass through the center of a circle, for the center of the circle, for the center of the circle. So we can actually implement all 15 in our drawing. Why? Because in our drawing we have, this is the common external point, point B, point A. From this common external point, point A, we have two tangents to this small circle, tangent AK and tangent AN and tangent AK. So by drawing those two tangents AN and AK, we created here angle A. Again, angle A was created by drawing tangent AK and AN to this small circle. According to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Again, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So she found out that the angle bisector of angle A passes through point found out the three that the angle bisector of angle A passes through point P. Here, this is the angle bisector BA, it of course passes through point P, that is the center of this small circle. We continue to focus on this convection point, point A. From this convection point, point A, we have two tangents to this big semicircle, tangent AEB and tangent AH. By drawing the two tangents AB and AH, we created the same angle A. Therefore, we can implement here rule 15. According to rule 15, the angle bisector of this angle A passes through point Q, that is the center of this big semicircle. Again, according to rule A, the angle bisector of angle A passes through point Q, that is the center of this big semicircle. So QA is the angle bisector of angle A, and of course it passes through point Q, that is the center of this big semicircle. And of course that this angle A, the angle bisector of this angle A passes through point A, that is the center, passes through point A. And again, if we found out that the angle bisector of angle A passes also through point A. So in conclusion, we found out actually that the angle bisector of this angle A passes through points A, P, and Q. Okay. And then again, the angle bisector of angle A passes through points A, P, and Q. But the angle bisector of any angle is a straight line. Therefore, we can write down that points A, P, and Q, they are all passing through a straight line. What is the straight line? The straight line is the angle bisector of angle A. Okay, so the points A, P, and Q, they are all passing through the same straight line. And therefore, they are all located on the same straight line. What is the straight line that are located? The straight line that are located is the straight line that is the angle bisector of angle A. Because the angle bisector of angle A is a straight line. Or we can say also that all the 3 points A, P, and Q, they are all located on the same straight line. The straight line is the angle bisector of angle A. Or we can also say that line segment APQ is one straight line. Again, line segment APQ is one straight line. And again, we found out that line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. If AQ is a straight line, it means that shape ABQ is a right angle. If AQ is a straight line, it means that shape ABQ is a right angle. Okay. Here, shape ABQ is a right triangle. So in the right triangle ABQ, if we define the size of angle A as 2 theta, then the angle bisector QA bisects angle A to 2 halves. Each half equals 2 theta. This is the first half and this is the second half. Likewise, The angle bisect OPA also bisect angle A into two halves. Each half equals 2 theta. This is the first half, this is the second half. So we can write down that angle theta is a common angle that belongs to both triangles. Angle theta belongs to the small right triangle ANP, and angle theta also belongs to the big right triangle ABQ. So in the big right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the small right triangle ANP, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta according to the sum rule, that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we proved that the right big triangle ABQ is similar to the right small triangle ANP. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both angles, so we can write down that angle theta equals to itself as a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all the triangles in the right big triangle ABQ are correspondingly equal to all the triangles of the right triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, we actually found out that the right big triangle ABQ is similar, this is the sign of similar to the right small triangle ANP according to angle similarity rule. And from the fact that the right big triangle ABQ is similar to the right small triangle ANP, we derive that the following relationship exists between their sides. We will derive side AB, the big right triangle ABQ, over side AN, the small right triangle ANP, equals to side BQ, the big right triangle ABQ, over side ANP, the small right triangle ANP. I repeat again, we will derive that side AB, the big right triangle ABQ, over side AN in the small right triangle ANP, equals to side BQ, the big right triangle ABQ, over side NP in the small right triangle ANP. AB is 6, again AB is 6, AN is the missing side, so we leave it as it is. BQ is 3, it is the radius of the big semicircle that is 3, over NP. NP is A, is the radius that we are looking for in this question. So in conclusion, we found out that 6 over AN equals to 3 over A. Here we cross multiply this equation, and finally found out that 6A equals to 3AN. Here we divided this equation by 3, and finally found out that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So this is the missing side AN that equals to 2A units in its name. So AB equals to 6, AN equals to 2A, therefore the missing 9, 7, and B must be equal to AB, that is 6, minus AN, that is 2A. So in total, A and B equals to 6 minus 2A. Okay, in the next step, from the center of this small circle, that is to say from point P, we draw perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we get quadrilateral NPBQ. Inside quadrilateral NPBQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the quadrilateral NPBZ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we relate to quadrilateral NPBZ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBZ, Side NP must be equal to the opposite side BZ, but NP equals to A, therefore BZ must be also equal to A. Likewise, according to the sum rule, in the sum rectangle NPBZ, side NB must be equal to the opposite side PZ, but NB equals to 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of the missing line segment QZ? QZ equals to BQ minus BZ. Again, QZ equals to BQ minus BZ. BQ is 3, BZ is 8, so in total QZ equals to 3 minus A. What is the length of PQ? Actually found out the length of PQ by implementing rule 10 in our drawing. Actually in our drawing we have an external arch between this small circle and this big semicircle. That is to say, they are touching each other externally at point L. And whenever you have an external arch between two circles, you can implement rule 10. I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the side line that connects their centers together must pass for their touching points. In the drawing we have two circles. Those two circles, they touch each other externally at point P. Therefore, we have an external arch between them at point P. The center of this small circle is there at point M. The center of this big circle is there at point O. And the side line that connects their centers together is of course the side line MO. And this side line MO must pass for point P, that is their touching point. Again, the side line MO must pass for point P, that is their touching point. Or MPO is one side line. Again, MPO is one side line. Actually, we can implement rule 10 in our drawing. Why? Because in our drawing we have an external arch between this small circle and this big semicircle. That is to say, they are touching each other externally at point L. Therefore, we can implement here rule 10. The center of the small circle is at point P. The center of this big semicircle is at point Q. And the side line that connects their centers together is of course the side line PQ. This side line PQ must pass for point L, that is their touching point. I repeat again, the side line PQ must pass for point L, that is their touching point, or PLQ is one side line. Again, PLQ is one side line. If PLQ is one side line, it means that PQ is a side line. So what is the length of PQ? PQ equals to PL plus LQ. Because of the fact that PLQ is one side line, it means that PQ equals to PL plus LQ. PQ equals to PL plus LQ. PL is the radius of this small circle A, that is the radius that we are looking for, plus LQ. LQ equals to 3, it is the radius of the big semicircle, is equals to 3. So in total, PQ equals to A plus 3. So the hypotenuse of the right triangle PZQ is A plus 3. Side PZ equals to 6 minus 2A, and side ZQ equals to 3 minus A. So in the next step, I copy the right green triangle PZQ in the new page and implemented the Pythagoras theorem in the right green triangle PZQ. So actually, this is the right big triangle, the right green triangle PZQ that I got from the original drawing. According to the Pythagoras theorem on the right green triangle, on this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square, that is the square of the hypotenuse, must equal to PZ square plus ZQ square. PQ is 3 plus A, therefore PQ square is 3 plus A square, and it must be equal to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square plus ZQ square. ZQ is 3 minus A, therefore ZQ is 3 minus A square. So in conclusion, I found out that according to the Pythagoras theorem in the right triangle PZQ, 3 plus A square equals to 6 minus 2A square plus 3 minus A square. Open the brackets on both sides of the equation and finally found out that 3 plus A square equals to 3 squared, that is 9, plus A squared plus 2 times 3 times A, that is 6A. On the other side of the equation we have 6 minus 2A squared. 6 minus 2A squared equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6, that is minus 12, times 2A, minus 12 times 2A is minus 24A, And we have here plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared minus 2 times 3 times a, that is minus 6a. Here we have 9 on both sides of the equation, so 9 we get cancelled, and we have also a squared on both sides of the equation, so a squared also we get cancelled. After we cancel those two expressions, in this side of the equation we have to leave with 6a. In the other side of the equation we have 36 plus 4a squared, and here we have minus 24a minus 6a is minus 30a. So in conclusion, we found out that 6a equals to 36 plus 4a squared minus 30a. Here we subtracted 6a from this equation, and finally found out that in this side of the equation we have to have nothing, 0. In the other side of the equation we have 36 plus 4a squared, and minus 38 minus 6a is minus 36a. So in conclusion, we found out that 0 equals to 36 plus 4a squared minus 36a. Here we divided this equation by 4, and finally found out that 4a squared over 4 is a squared, and we have here minus 36a over 4 is minus 9a, and 36 over 4 is 9. So in conclusion, we found out that a squared minus 9a plus 9 equals to 0. This is a quadratic equation. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula for quadratic equation, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus 4 to b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a, so x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 9, and the coefficient c equals to 9. Okay, the coefficient c equals to 9. So the only thing that is left to do is to put the data of our specific quadratic equation inside the general formula for x in order to find out the values of a, because x equals to a. So we did it and found out, okay, again x equals to a, so a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus 4 to b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 over 2a. A is 1, so 2a is 2 times 1, that is 2. So we found out that a equals to 9 plus minus. Inside the root we have 81 minus 36, that is 45. So inside the root we left only with 45 over 2. So here we have two solutions that are possible for a. The first solution for a is the radius of this small circle, that is the radius that we are looking for in this question. The radius a of the small circle equals to 9 plus minus 4 to 45 over 2. This expression is greater, this expression 9 plus 4 to 45 over 2 is greater than 3. So it means that according to the first solution, the radius a of this small circle is greater than 3 units, but the radius of this small circle cannot be greater than 3 because of the fact that the radius of the big semicircle equals to 3 units. And the big semicircle is definitely greater than the small semicircle, and then the small circle. And therefore, the radius of the small circle must be smaller than the radius of the big semicircle, that is 3. So the radius of the small circle must be smaller than 3. So this solution that gives us that the radius of the small circle is greater than 3 is the incorrect solution. So we cancel the solution and we left only with the second solution that is possible for a. The second solution for a, that is the radius of the small circle equals to 9 minus 4 to 45 over 2. So the radius a of the small circle equals to 9 minus, we substitute 45 by 9 times 5 divided by 2. The square root of 9 is 3, so inside the root we left only with 5. So we found out that the radius of this small circle A equals to either 9 minus 3 times 4 to 5 over 2 units, or in terms of numbers, the radius A of this small circle equals to 1.146 units in its length. That is less than 3 units. Okay, thank you very much.